Hello all and welcome back to this course on computer organization. So having looked at the single cycle RISC V architecture and also the multi-cycle architecture, we are now going to jump into the most commonly used and most efficient architecture, which is basically the pipelined architecture. Okay, so let us summarize what we have seen till now. What we saw is single cycle, right? The idea in a single cycle processor was you can have a pretty long clock period, right? Uh, right? This is one way to sort of, okay? Okay, and the processor would simply execute instruction 1, instruction 2, right? 1, instruction 2 in a single clock cycle. Every instruction just takes a single clock cycle, right? So this is basically the single cycle execution. Okay. So the idea of moving to multi-cycle is the clock can technically be broken into smaller periods. Okay. I could even do nearly half the period, but it need not be exactly half. Right. So this is how the single cycle clock multi-cycle, right, MC. So basically you say I will do, some instructions could just take one clock cycle. By the way, does everything need not take multiple clock cycles, right? I could have something like this, instruction 1, and the next instruction, because it's a different type of instruction, right, could take 2 clock cycles, and then you're back to the single cycle, right? No, so this is wrong. So let me redraw this. So this is also taking just one cycle. Okay, and we are now looking at this you launch, then you have another clock cycle, and this is going to take about 2 clock cycles like this. Okay, this is my instruction. This is my multi-cycle. Okay, and effectively what we are basically saying is this could technically speed up the program execution time because of the one clock period is coming down, and therefore you might increase the average cycles per instruction. However, if most of the instructions in that load happen to be completed in one clock cycle, which is smaller, you might get a benefit in terms of program execution time, right? So this seems like a very reasonable implementation. However, what we are actually assuming here, right, if you look at this, this is the whatever bus I am showing here and here is basically the microprocessor is active doing something in that phase. Okay, what is interesting to note is we moved from a single cycle processor to a multi-cycle processor by inserting flip-flops in between them. Okay, so what I'll do here, right, is to go back and maybe get one of these the single cycle block diagrams that I can use for analysis here. Okay, so let me just get that and then come back here. Yeah, I'll use this diagram as usual, which can be used to explain this idea very nicely. Yeah, So this is the single cycle implementation that we had looked at earlier, right? Single cycle architecture. Okay, and what did we do in order to make this a multi-cycle implementation? We said the first thing that we need to do is to sort of introduce flip-flops, okay, at the point in each of these whole at different points, so that you can hold the data while that operation is being performed. So what we did was, we said we will introduce a flip-flop here, okay, where you are getting the instruction and then the instruction is being held for you, right? So likewise you go through this whole thing, then after register file we said you could do it, after the ALU you could do it. So by the way, the multi-cycle implementation is, there is no necessity that you have to place the flip-flop after every single combinational block. You could combine some combinational blocks also. For example, in this case I am just assuming that decode, register file and ALU is happening in one shot as one combinational block, and then I am putting a flip-flop after the ALU result, okay. So this will be a different multi-cycle implementation from what we had discussed earlier, and why is that? Because of the place and the number of flip-flops that we had used, okay. So let me just show you this diagram here, right? If I show you this thing here, it will become very evident to you, right? So what you see here is we have put in a flip-flop, okay, right after the instruction memory out here, okay, and then we added another flip-flop after the register file and another flip-flop after the ALU result. But the point I am trying to make is, what I have drawn here is I have removed that flip-flop after the register file. So I could technically combine those two combinational blocks of register file, decoder, extender and all that, and then put it along with the ALU and then put a flip-flop after that. This might not be the most efficient implementation, but this is also another valid multi-cycle implementation whose performance will be determined again by the slowest path between the launch and capture flop appropriately, okay. So like that you go ahead and add these flip-flops and we are doing something very interesting. So in the multi-cycle case, okay, what we have done is we have basically taken this whole flip-flop, this big combinational circuit in the single cycle execution, okay, and I could replace it by a combinational block called fetch, okay. So this is my program counter clock, okay. Then I am putting one flip-flop here, okay, clock. Then I have the register, I will call it decode actually. Why? Because the input bits that are coming are being used to decode the registers and the arguments to the ALU and all that. So there is a decode, and in this particular example I happen to combine the ALU also here, okay, and then I am putting a flop here, okay, and then there is a whole memory write back that needs to happen and stuff like that. So let's just look at part of this execution unit data path and then we'll understand what is the problem here, right? So what we are doing is, we are saying we are going to fetch an instruction, we are going to decode, we are going to do an ALU, right, operation, and then we are going to maybe do a memory write back and all that, right? And all these things are happening in different clock cycles, okay. That is the key point for us to remember here. So in some cases you might be fetching, you might be decoding, and then there might be no memory write back. I mean, if it's a store word, you might have a memory write back. Otherwise, you do some memory read, load, and then come back and write the data back into the register file. That could be the register write back phase. Okay, but what is actually happening is that while this decode and ALU units are executing that particular instruction in the multi-cycle processor, this fetch unit is still doing nothing. Okay, that's why if you look at this particular timing diagram that we drew here, okay, we are saying that instruction 1 was executed in this clock cycle. This is instruction 2. This is instruction 3. Okay, it is taking some 2 clock cycles something, but effectively if you look at what is happening in instruction 3, right, it is effectively going to happen in this particular way. Okay, again this instruction 1 and instruction 2 can execute in a single cycle only if you fetch, decode and execute in one shot. Okay, only the register write back or memory operation can be separated out. Okay, only then at least that R type instruction or something can be executed like this, right? Nevertheless, what is happening here is this clock cycle, right, where you are doing instruction 3, the first half of this thing, you have already done this fetch, decode and execute. FDE you are doing for that instruction, and memory, what you are probably doing in this phase is register write back. Okay, you are doing only the register write back in this particular phase here. Okay, but while this register write back phase is happening, this, you know, the part of the circuit which did the fetch, decode and execute, right, is technically doing nothing, right, though it can be used because there is a flip flop for you to hold the data at the point where register write back has to happen. The previous stage is still doing nothing and it is waiting for this instruction to complete. In fact, that is why it is okay for every instruction to take different number of clock cycles. Some may finish in 2, some may finish in 3, 4 and all that. That is because the system is waiting until the next instruction comes in, then you do the decoding, figure out how many clock cycles and then go back, right. So, in some sense what we are saying is, while this part of the hardware is being executed, right, this part is remaining idle. Okay, these two happen in 2 different clock cycles, but yet that part of the hardware is remaining idle, and therefore any idle time is going to cost your program execution time eventually. The figure of merit of your microprocessor will drop because of this idle time. Earlier also we saw the idea was to reduce the idle time when you try to go from single cycle to multi-cycle. Therefore, in order to improve on this, what we technically need to do is to start using and make this part of the circuit busy while you are executing some previous instruction in the next part of the circuit, and that precisely is the concept of pipelining. Okay, so what we are going to jump into is basically the pipelined RISC V processor. Okay, this is the most commonly used implementation now. Okay, and what we want to do now is to move to a pipelined RISC V implementation. Okay, so let's look at what's going to happen here, right. So basically what we want to do is known as temporal parallelism, in the sense we want different blocks to all be active at the same time. Yes, they may be operating on different instructions at this time at that instant of time, but that is exactly what we want. We don't want anything to be idle at that point. So therefore what we are going to do is we are going to divide the single cycle processor into 5 stages. That means we are going to put flip-flops in 5 places so that you can hold that data for that cycle. After you fetch, after you decode, execute. So decode is basically the control and the register file part. Execute is just the ALU. Then you do memory operation, right? You may have to access data memory, right? And then you're going to do a write back, which is basically register write back here, right? So we are going to add pipeline registers between the stages, okay? So what is shown here is basically the idea and difference between a single cycle execution and a multi-cycle execution, okay? So if you look at this, we are talking about the time on the x-axis in picoseconds, and somewhere near 680 picoseconds is where the single cycle clock frequency is, clock period is, okay? So we are saying assume that the instruction fetch is going to take 200 picoseconds, decode and read nearly 100, execute is slightly 120, right? Memory read again is 200 picoseconds and so on, and register write back has a that whole mux plus setup and all is there, right? That is going to take you some time. So all these individual blocks that you see here, right? These individual blocks that you see are basically combinational delays, okay, and which were all adding up in the single cycle execution, and therefore we got a period of nearly 680 picoseconds or whatever, right? Then the next instruction obviously in single cycle can happen only in the next clock cycle, right? And therefore again you do the fetch instruction, you decode the read registers, right? Then you do execute the ALU, again memory read or write, and then you write the registers back, okay? So what we are now doing, right, is we are going to say, look, I will make the clock period, okay, some particular amount of time, okay, and I am going to decode, fetch, decode, execute, do memory write back and register write back in different clock cycles, okay. And if you look at it, the sequence of operations is you have fetched instruction 1, okay, then you have decoded the read registers, and then you are executing the ALU, okay, then you are doing memory read and write, and then you are writing the register back. So what is interesting to note is while the fetch and fetch instruction is being executed for instruction 2, you note that the decode is already being executed for the previous instruction, instruction 1. So while that execution is happening on instruction 1, the previous stage which was supposed to fetch is now going to go to memory and fetch that next instruction already, okay. So first of all, I have different combinational blocks, okay, out here. So let me put that down out here for you, right? So I am now going to break this pipeline implementation into 5 different stages, okay. So I have the fetch, right? Fetch is basically a memory read operation from the instruction memory, right? Then I have register decode, I'll just call it decode, okay. Then I have my execute, okay, and then I have I have memory. Again we are talking of memory read, right, is the slowest operation there. Then I have register write back, right, and eventually it's going back to this whole thing, okay. So now what we need to do is first understand how fast can this clock be. Okay, the fetch, if you look at it, we are talking of is a memory read. So it's about 200 picoseconds, talking of 200 picoseconds here. The decode is basically going to go through the register file. There is a decode, you remember that whole critical path and all that we spoke about. So therefore typically this was going to be limited by the RF read part, and that was about 100 picoseconds, right, the T register file read. And then the execute on the other hand was just the ALU delay, which is 120. Then this was back to 200, and then the write back is basically just the feedback part, some multiplexer plus this register file delay, right. So we had about 60 picoseconds plus some 30, so maybe I would say 90. So if you look at this picture here, it's very nicely represented because the width of that block actually is telling you when the decode is decode, read register and all this that stuff is happening, right, and execute ALU is going to take some time, right, and the memory read and write and all that stuff is happening here. Okay, so I will come to this, the reason why there is a gap in this fetch, after fetch instruction before the decode read register. Okay, I will come to that a little later. That's an involved concept, so I will get to that in some time, right. But effectively now if you ask me what is the clock frequency at which you can operate this, right, it really goes back to our static timing analysis, where we said that when the moment I start pipelining, the clock frequency is going to be determined by the slowest combinational block between any launch and capture flop. So if you look at this, we are now talking of these two stages, right, being about very similar in terms of delay. That's why you see that memory read write block and fetch instruction have similar width of nearly 200 picoseconds, right. So therefore we are now going to assume that the clock period here is going to be of minimum at least 200 picoseconds, right. So therefore only then the system will work. So I am saying I have a clock like this here. Okay, this is my clock. Okay, so I am saying this is going to be 0, 200, 400, 600, 800 and 1000, right. So therefore if you look at the execution time for a single instruction, it is going to be 1000 picoseconds, because it's going to take about 5 clock cycles for it to go through these 5 pipelining stages. Okay, this is because we broke this into 5 pipelining stages. So this is also evident to you why you should not break something down beyond a certain granularity. Okay, so look at this. For example, this fetch is 200, decode and execute happens to be about 100, 120 and stuff like that, right. Technically if you combine decode and execute, that may not be that bad an idea also. You could make a pipeline stage where you are combining those two blocks, but we will not get into that for now, right. But because some blocks are much faster than the other, you will end up wasting some time idling. For example, the write back may happen very quickly, right, 90 picoseconds you're done, but then what do you do? The clock has to be determined by the slowest block and therefore you have to wait. Okay, so therefore you will not try to push this pipelining idea beyond this and try to make it work at a much smaller frequency, because the execution time ultimately is what matters. Okay, therefore it will take 1000 picoseconds for the first instruction, right. Instruction 1 is going to take 1000 picoseconds to go through this whole process. The advantage with pipelining, as you saw during the static timing analysis discussion that we had, was that you can now pump in the next instruction 200 picoseconds later. Okay, as opposed to what you would do in a single cycle or even multi-cycle. You are not waiting for that instruction to complete across multiple clock cycles. The moment you go to a next clock cycle, you pump in the next instruction, and therefore you can continue with this. So instruction 1 would basically start here, right? Instruction 1, instruction 2 would basically start right here. So this is the fetch, right? This is the decode. So instruction 2's fetch is happening in the second clock cycle, right? This is the execute here. During the execution of instruction 1, my decode of instruction 2 is happening, right? And so on, right? So that is exactly what is depicted in this particular diagram, right? You are able to do the fetch while decoding is happening for the first instruction. The third instruction is happening in the next clock cycle. 400 picoseconds, next instruction comes in. While that is fetching, instruction 2's decode is happening, instruction 1's execution is already happening in the ALU, right? Likewise, you take all of this. So therefore, every 200 picoseconds, you are basically going to come up with, you will be able to get the result of some instruction or the other over time if you wait long enough, right? So the throughput of this system is going to be 200 picoseconds, right? Is going to come out, there will be an output, one output every 200 picoseconds. But the latency of one instruction is still 5 clock cycles, and therefore we are talking of 1000 picoseconds here, right?